Okay, so at the last class we started talking about PCE to TCE to cis-DC to vinyl chloride. So these are all DNAPLs, and this is probably the second most contamination event that people deal with. Usually BTEX compounds, and we'll get into BTEX in a little bit here, but gasoline spills are like number one. This is dry cleaners, so these compounds were dumped into the environment a lot. So when we talk about civil action, this will be it. So we ended the discussion on Friday about vinyl chloride, and so I just wanted to pick up, because I ran out of time on my recording. So I just wanted to pick it up a little bit from there and go on a little bit. So again, when we talk about this degrades down to vinyl chloride is this compound here. So where it's got one chloro group on top of it is called vinyl chloride. Again, why is it called vinyl chloride? Well, that's the older name for it, and that's what we call it. There's probably some in the scheme of things why this is called. It could also be referred to as chloroethene, but no one says that. So we call that vinyl chloride. And then when we put them together, we make what's called PVC, polyvinyl chloride. So I was going to show you guys on the interwebs here. So what's the difference between them? So here's vinyl chloride, C2H2, and you get one of these. And then when you get polyvinyl chloride, it's just this mixed together. And so this makes PVC pipes. So this is what PVC, all those plastic pipes that you have inside of your house, this is what it's made out of. This is the functional group that's in there. And then you just connect another one of these onto here, and then on and on and on and on, and you get plastic, or the polyvinyl chloride. One of the things that you'll notice about these compounds, and this is just one of the little side notes about this, is all of these compounds have that halogen into it, that compounds that are on the, let's see if I can do this here. If you guys look at my periodic table of elements, they're the second row here. Those are your compounds inside of your halogens in there. Well, your halogens, when you mix those with carbon, they are a man-made compound. So no matter what you see, when you see that, you know it's man-made. Almost all of them, and I can't think of one that isn't, really toxic to the environment from multiple different ways. So like this is from the EPA, so this is our drinking water regulation, so this is the MCLs for these compounds. And we can look at vinyl chloride here. This is the MCL, this is the MCLG, which is the goal. So you don't want to have any in your water, but the MCL for it is 2 ppb, or 0.002 ppm. If you notice, what happens is an increased risk of cancer, leaching from PVC pipes. So all of those PVC pipes could actually leach and give you, discharge from plastic factories is very common to get vinyl chloride. Also, when you have degradation of TCE, it'll accumulate this. This compound is a gas, and so a lot of times what will happen is this compound will then get up into basements. If there was a TCE spill, you can get this into there and you're breathing it in. If you notice, just on looking at this list, here's trichloroethylene. The MCL is 5 ppb. In there, causes liver cancer, increased risk. Metal degreasing sites and other factories, very common into there. But if you look up here, if you notice the word chloro, and you guys should be able to draw 1,2 trichloroethane. Simple, right? 1,1 trichloroethylene, 1,2,4 trichloro. Oh, well, we'll get into benzene here in a second. But if you look at all of these things, when you have this carbon-chloro bond, it's man-made. It is cancer-causing. So when you see that, that should just set up a red flag to you that this is probably a bad compound from a health point of view. Also, the chlorine, when it chlorides, when it goes and gets released into the environment, we could talk about the hole in the ozone layer. And so a lot of these compounds, especially when they become gases, if they get into our atmosphere, they are part of our problem with our hole in our ozone layer and can cause degradation of our ozone. We could spend a whole time, this class is not on that kind of a topic, but we could talk about the hole in the ozone layer. But I just wanted to point these things out to you. So when we look at this, this is cancer MCL. So whenever you see this in any of our compounds coming up, know that it is a man-made. Originally back in the 1950s, it was better living through chemistry. Everything could be solved with chemistry. So when we get into like the devil we know and all these other compounds, it's going to be this constant reminder of, wow, isn't this a great compound? This is great. And now we realize how bad it is. So that is one of the morals of the story, is always be careful when they say, we have this brand new thing, it's going to save the world. We'll talk about MTBE with that too. Okay, so let's get back onto our lectures now. Okay, so I'm using a green pen because I'm wearing green today, so I've got to match and coordinate my outfits. I picked up a green one, but yeah, it could be fun to do that too. Okay, so when we're talking about these compounds, one thing I wanted to kind of get back, do a little step back in, is when we're talking about these compounds, we're going to be talking about like the structural formulas. So when we do the structural formulas of these compounds and stuff like that, if we do just the molecular formula, it just tells us how many carbons there are, how many, like C6H6O, H12O6. I mean, this is glucose. But it doesn't tell us about where anything is. It doesn't tell us how it looks or anything like that. It just gives us the numbers of carbons and everything like that. We actually prefer the structural formula, which shows the arrangement. So structural formulas actually shows the arrangement, which is much more important, especially now that you're kind of seeing why we need to know the structural arrangement of these compounds. Becomes a lot more interesting and tells us a lot more about the compound. So it shows us where the bonds are into there. So, instead of writing, so like another example here would be, butane. So butane could be written as CH3, CH2, CH2, CH3. And so it just tells us where everything is and how it's in there. Now you can do what's called the condensed version of this compound, and this is perfectly fine, where you go CH3, parentheses, CH2, parentheses, 2, CH3. Now, for the small compounds, it's not a big deal, but say I give you something that's like, decane or something like that, where you have like 10 carbons in a row. You don't want to write out CH2, 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 all those times. So you can do this. This is called the condensed version of it. So this is perfectly fine to use into there. And the structural formulas become really important too, because it tells you where like those branches are. So we could write out a compound like this. We could write CH3, CH3, CH, CH2, 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 CH3. Or we could write this as CH3 condensed, CH, CH2, 3, CH3. Okay? So both of them are perfectly fine. You can write them however you'd like. Okay? So that's the structural formulas. The other thing that you can do is what's called the bond line structure. That's where I've been drawing like something like this. Okay, where I don't represent all the hydrogens, I'm just showing the doubles and single bonds, I'm just, the number of carbons that are in there. And so what are some of the rules for about doing the bond line structure? Well, first of all, the carbon atoms are not shown unless needed for special emphasis or clarity. So we don't show all the carbons. So one, no carbons unless there's, needed for special clarity. Okay? All other atoms other than carbon and hydrogen are explicitly shown. So no carbon, all others are shown. All others shown. Okay, so the chloros, whatever else is in there. A carbon atom is assumed located at the end of each line segment or at the intersection of two or more lines, which are used to depict the bond. So carbon at end or intersection. So this would be like when I was doing this is assumed 1, 2, 3, 4, 5. Okay. Multiple bonds are shown with multiple lines. So multiple lines, multiple bonds. So we show dot dot for a double bond, which you've already kind of seen. and the proper number of hydrogens to provide 4 bonds to each carbon is implied. Hydrogen to other atoms such as oxygen and nitrogen are implicitly indicated. Okay, so an example, so that one just says that you don't have to draw out those little hydrogens. So much faster than drawing these type of things up in here is drawing these bond lines and stuff. So we could do no H. So what we can do is we can go CH3, CH2, CHBr, CH3, or we could write CH3, CH2, CHBr, CH3, or we can go 1, 2, 3, 4, 1, 2, 3, 4, bam, we're done. So much, much quicker into there. Now, anything else you show onto there. So so any of these are correct. You can pick however you'd like to do it. If you prefer to use the structural formulas, the bond length. I'm going to be mixing and matching them because I think you need to learn all the different ways that these things need to be put together into there.